Good afternoon, everyone, and welcome to our noon meeting, which is a hybrid online as well as contact meeting. The Occupational Medicine Division is hosting this particular noon meeting, and we are very honored to have Dr. Greg Kew, who is going to present findings of his MSc dissertation. And the title of his dissertation was a study to characterize the arsenic rash observed at a copper smelter. Where was this? In
Sumet.
In Sumet. Okay. And he was even what can I say? He had also the pleasure of having two of our eminent supervisors who are emeritus professors from our UCT Occupational Medicine Division, Prof. Johnny Myers, who is also online, and Professor Gail Todd, who also co-supervised. And I'm reliably informed that Greg did very well in his dissertation and passed. So informally, we are also celebrating the passing of his dissertation. Well done, Greg. Over to you.
Thank you so much. Thanks for that. I'm going to stay here so that I can operate the slides. Just as the two comments on this slide. Firstly, notice the dates, 2017, 2018. So my thanks to my supervisors for their endurance and their willingness to walk the journey. It was a long and hard and arduous process. And to Mohammed, who's there supporting me along the way, shouting every now and then, saying, Greg, when's this going to finish? Is this a double PhD or is this a master's? But in truth, it was, I'll explain perhaps along the way why some of it was a bit delayed. But so thanks to these two eminent professors. I think they both retired because of me. They realized that this was just too difficult a thing to do. In fact, that's not true. They were retired before, but I am very, very honored to have had them guiding me. This was a slide that I was thinking of putting in, then took out, and then in the last minute put it back. I'm convinced that the entire purpose of a master's thesis is to remind one to be humble of the rigorous nature of academic research, and to bring humility to anyone who tries this enterprise, and renewed respect for those of you who are in the game of research and publishing. So truly, truly respect to you in academia. The quick overview of the talk is sort of along the lines of the traditional headings in the thesis. So a bit of an introduction to arsenic generally, the plant, and then the key objectives and so on. So let's get on with it. This is where it all is. So if you don't know where Tsumeb is, it's in Namibia. It's quite north of Windhoek, so it is quite difficult to get there. One of the constraints of this particular research was to share access to the place. They are a place that receives complex ore concentrates from various places in the world, and they produce copper. The main arsenic as a byproduct is, in fact, arsenic trioxide. We'll talk about that just now. Couple of pointers. One is that it's hot and dry, both of which are kind of relevant for today's talk. If you look at the temperatures, sort of in the 30s, 33s most of the time in the upper end, and then dropping down to a cool 8, but mostly quite warm, and also not much rainfall. So the hot and dry results in sweating, and the sweating and occlusion is clearly a risk factor for dermatological problems. And because they're working in an environment with arsenic trioxide, these half-mask respirators are permanently worn all the time by people on the plant. So hot, dry, permanent mask, misery. These are the respirators in use. The other PPE would be a hard hat, goggles, and overalls and boots. This is a common practice on the smelter. They wear this material covering around their head and neck in order to protect from what it is to help absorb the sweat, and that occlusiveness of the protective equipment in is minimized. It was generally regarded as a no-no on the plant until relatively recently. I think, in fact, perhaps as a consequence of the study. So that material cloth covering was a no-no because, of course, it interferes with the integrity of the respiratory protective equipment, as all of you would know in this audience. So these are the sort of scenes from the smelter, very hot, these fugitive emissions from time to time, arduous work. A quick overview of the smelting process. So this is the receiving bay where those those concentrates and the various components are received. They get fed through to the furnace. The first furnace is called a TSL, or a top submerged lance furnace. So it gets put onto a large structure that goes down into the furnace itself. It's charged and it generates a charge which fires up heavy furnace oil plus the concentrates. And then that plus oxygen results in a powerful exothermic reactions. And then there's off gases produced from that, but there's a second step where the mat is the good stuff. It's the juicy stuff that's got copper in it. It's fed along here to a second a converter furnace called the Pearce-Smith converter furnace, where it gets burned again. So here air is added to the mat, oxygen reacts with sulfurs, and the sulfurs from the metal sulfides have an exothermic reaction, and that results in the much more pure 98% blister copper that gets sold. In the meantime, these off gases here, which are perhaps a bit small on the screen, but those are the off gases. So it's the sublimated gases that are generated as a result of this heat, go through evaporative coolers, where then the off gas has particulate, and in that particulate it forms dust. The dust is filtered into these bag houses. There's a bag house for the Arsenic, which is the TSL furnace, a bag house for the Pearce-Smith converter, and there's even a bag house for this here, which is the arsenic plant. Now, what is that? Well, these dusts that are collected are transported to this plant because this dust contains arsenic trioxide, and quite a lot of the arsenic trioxide, and that's collected here, is processed twice through these things called roasters. They even call it the arsenic kitchen, which is a bit of an oddity to call something that's highly toxic, but it's just a colloquial term. They're roasted, and the kitchen gets roasted twice, and then the pure powder that comes from that is arsenic trioxide, which also, in fact, gets sold to a market, particularly the pesticides and wood treatment market. In the meantime, there's another gas that comes off as a sort of an off gas, sulfur dioxide, which is a big problem too, because if it gets sent into atmosphere, then the local community complains because all their plants die and they get H2SO4 fallout. So SO2 gas release as part of this, particularly from the second step, it can be a problem, but they've since built a sulfuric acid plant, smartly gathers up all that SO2, converts it to SO2, releases a clean gas, and SO2 is sold to the mining industry. So that's the general process. There's a slag that comes off. So when you smelt, there's slag, which is the unhelpful stuff. But that gets recycled because there's some copper still remaining in there, but eventually the residual goes to waste. So slag to waste, that's the main last bit to mention. The rash hotspots, where generally the stats seem to show them, happen on particularly the bag houses. So the Arsenic bag house, the converted bag house, this effluent treatment plant, less so, but it was in the mix because they had a couple of cases there, and it was almost kind of why, because it's a liquid format there. There's not really powder. And then the arsenic plant. So those are typically where the powder or dusts end up, and then the effluent treatment plant is more like a cake. So what problems were we wanting to solve? This is a working smelter, working issues, and part of the reasons for this was to try and solve problems. So firstly, whilst it's not a daily occurrence, the skin rashes happen several times a month in terms of the monthly stats. And the question is, what is the underpinning of this rash? It's always been simply attributed to arsenic. So it's called the arsenic rash by everybody in the plant. But the question was, well, is it really, and what actually is it? And the second connected question, is it because of an allergy to arsenic? Is arsenic, are people allergic to the arsenic? And that has an implication perhaps in medical surveillance, and who can work there and who can't work there, and some sort of screening. Allergy different to irritant. The occupational health staff also felt that there was a link between that and poor hygiene and hand practice, so that there was a non-compliance in the sense that putting people at risk. And also that they should be using these jolly barrier creams, and because they weren't using barrier creams, that's why they were getting these rashes. So of course, if Gail here was listening, she'd be hopping up and down in the mention of berry creams. But nonetheless, it was in the mix. And the staff and employees also felt that there seemed to be a link between PPE, using it or not using it. So instructed to explore some of those links between PPE and rash risk. And then lastly, these baghouse dusts. What is the link between a baghouse dust? There's clearly a higher likelihood of getting a rash if you're exposed to baghouse dust. But what is it exactly about that baghouse dust? Is it the arsenic? Is it something else? And so that is part of the driver for the study. So the objectives then were kind of listed like this. The first was through some sort of exploratory questionnaire. The first two things would be to look: is there a possibility that pre-existing allergy might be a risk factor? What about the skin hygiene and hand cleaning practices in the smelter? What about the use of barrier creams? And what about the use of PPE itself? Then there was a more technical sequence. This one here being looking at the actual chemical constituents themselves. What is in these dusts to which people are exposed? And would that help to shed some light on what's going on? Once that was done, then what about the dermatological response to these exposures? Is it irritant or is it allergic? And finally, is there something in this baghouse dust? Can we draw some conclusions from the above about what's in the dust and the reactions? So that's the background. So a quick launch into a bit of stuff about arsenic. So bear with me over the next couple of slides. Just a bit of background. Remembering that it's ubiquitous. Arsenic is always linked with poisons and toxins and killing people and what have you, but it's actually everywhere. It's ubiquitous. It's the 20th most abundant element on the Earth's crust, incidentally. Typically located around areas of volcanic activity. And there are natural sources, man-made sources, which I'll talk about just very briefly again just now. But basically in soil and rock formations, you get inorganic forms in the sulfides and oxide complexes in soil, and then an organic form in fish, which is widely prevalent in fish worldwide. Then the man-made sources, particularly smelting, probably the biggest contributor of arsenic from a man-made point of view. Smelting of these metal ores, primarily copper, which is talked today. And then insecticides with preservatives. So as these folks make arsenic trioxide, it goes into all of these end products, and that ends up out there in use in society and in the environment. Incidentally, the World Health Organization has put arsenic as one of the top 10 chemicals of major public concern worldwide, and the International Agency of Risk Control has classified it as a class 1 carcinogen, which is not really the subject of today's talk, but obviously a relevant background. Point skin, liver, lungs, bladder, and kidney as the primary organs of carcinogenicity. It's a metalloid, and if you've forgotten what a metalloid is, it is on the periodic table. It sits amongst the metalloids, the yellow ones. There's arsenic. And a metalloid has a sort of an in-between characteristic between metals and non-metals. I just found the chemistry of arsenic quite bewildering, I have to say. If you just look at this, for example, the sort of quick overview of arsenic generally. So it exists in these 4 main valency states, which is really how the electrons are in relation to the protons and neutrons. These 4, here's arsine, which we've all heard as a highly toxic chemical. It's a gas and causes hemolysis. But in fact, it occurs in nature too. So it's basically a combination of arsenic and hydrogen. And if it's inorganic arsenic, which exists here in nature, if that combines with a weak base or weak acid, even in nature, you can get this arsine created naturally. It has a strange valency of -3, whereas these two, the main arsenics out there, are in +3 and +5. So trivalent arsenic, pentavalent arsenic. This is trivalent, but -3, and that's arsenic. Arsenic, the neutral form, obviously exists. It's relatively rare. These are very rare in nature. These are very prominent out there. So the moment you add any element except carbon, you've got inorganic arsenic. It can be inorganic trivalent or pentavalent, and it occurs naturally in, as I said, this arsenic-bearing minerals and ores. And these are names which I'm not going to repeat, but these have got names for the geology-minded people. And then the human-made versions of inorganic arsenic, by far the most common being arsenic trioxide, which is today's talk, created by smelters. And then organic arsenic, as I said, in fish, and human-made organic, you just add carbon instead of any other element, and you've got an organic version of arsenic. And the big ones here are the pesticides. And also, in fact, in wood preservatives, CCA in wood preservatives. Quick review of toxicokinetics. It's not that critical for today, but just any talk on arsenic will be incomplete without it. It's poor arsenic trioxide, by the way, is what we talk about. Poorly absorbed because it's poorly soluble in water. And generally we breathe it in, gets absorbed in that pathway, or through mucociliary clearance, it gets brought back up again and we swallow, and that gets absorbed gastrointestinally. So those are two routes of absorption. It gets distributed widely throughout the body, pretty much every organ system, crosses the placenta, and sometimes ends up in these keratin-rich structures. It ends up in the skin, hair, and nails, which are media through which exposure can be tracked. Generally, it's quite rapidly excreted and quite efficiently. About half in 3 to 5 days is all gone, but slower, this proportion that sits in the skin, nails, and hair is released more slowly. But our bodies are pretty good at metabolizing and excreting arsenic. It's metabolized primarily in the liver through a series of reduction and oxidation sequences, taking us from arsenic in both forms, whether it's pentavalent or trivalent, into these methylated versions called monomethyl arsenic or dimethyl arsenic, and then it's excreted in proportions like this. So that's a quick overview. So a little bit about the literature review, and it's worth mentioning, one of the reasons why we did this at all is that very little literature gets published for occupation exposure. Interesting. There were 8 studies found after looking very hard, and I'll share them briefly with you now, and they go back to the 1920s. But if you look at publications for public arsenic exposure, and talking about cities and populations, there are too many to count. So it's just worth mentioning that a literature review for occupation exposure is quite tricky. And particularly if you're looking for dermal effects of occupation exposure. So way back in the 1800s already, there was medicinal use of arsenic for pretty much anything. So it meant that a lot of people had arsenic exposure, and the most common form of this was fowler solution. And some of you might even still have come across fowler solution in your medical training days. I remember hearing about it, which probably puts me in a particular age category. But it was first popularized by this chap, Thomas Fowler, back in the 1800s. And it's got arsenic trioxide in it, diluted, dissolved with potassium bicarbonate and tincture of lavender. So after long-term administration, particularly orally or otherwise, these skin lesions were picked up. Palmar and plantar hyperkeratosis and these pigmentary changes, which we'll look at just now. So these are the first 4, starting from 1920, where this chap Dunlap had a look, and I think he was particularly looking at arsenic dust collecting in the nasal septum, and he was the first person to describe localized ulceration of nasal mucosa as a result of damaged blood supply, erosion, corrosion of the nasal septum, and these forming these ulcers. And Downing, in a few years later, reported case of chronic arsenic poisoning from the medications. This is essentially the person who did this research, coming up with the links between medications such as powders and creating dermatitis with these papules, vesicles, and pigmentation. And a long gap between Downing and Holmquist, the next study, looking at a big study, looking at workers over a 2-year period. And interestingly, Holmquist was the first and only person to identify contact allergy. Published this paper, it's still quoted constantly today. He noted that 80% of people who were sensitized, so on periodic medicals, 80% of them showed reactivity or increased reactivity to these chemical agents. But he was looking at arsenic, sodium arsenic, arsenate, and pentoxides. These are very highly soluble, as opposed to trioxide, which is not. And only 35% of people who were new and unexposed to it. So made a postulation that there was previous sensitization, and therefore he called it contact allergy. And then since then, that's not really ever happened again. Pinto and McGill in 53, another big study, 2 big copper smelters in Denver and Washington, where he described classic contact irritant dermatitis and a very similar experience of the sort of thing we were seeing at the smelter in Namibia. Clinical, and they're the usual hyperpigmentation. Let me just say this again. All the usual irritancy was noted, but they didn't find the classic signs, which I'm going to describe to you just now, of what we call arsenicosis. Arsenicosis is a sign of chronic exposure with classic features, and I'm going to show you pictures just now. And interestingly, in his study, they found no case of hyperpigmentation and keratosis, and noted that they didn't find evidence of clinical systemic toxicity, even though, well, let's say rarely found, even though the people exposed over a long period of time. And we need to talk about that briefly just now. Birmingham in 1964 basically also found contact dermatitis, and he also looked for allergy and couldn't find really it playing a major role. Did find a bit of nasal septum ulceration. So contact dermatitis. Wahlberg and Bowman, they also looked at sodium arsenate and arsenite, so they tried to repeat what Holmquist had found again. There was a small range of positivity small proportion of positive, but basically it seemed probably a cross-reactivity with nickel. They also couldn't find really strong evidence of sensitization. They repeated the study on guinea pigs, and again, no evidence of sensitization. Gonzalo in 89 found classic irritant dermatitis as well on arsenic trioxide. I'm not going to go through it in detail. And Mohammed, 1998, also using trioxide found classic irritant dermatitis. So substantive evidence for irritancy, and again, but there's this limited suggestion of allergenicity, but it lingers on as a possibility. So this is arsenicokeratosis, which is the classic sort of thing you find when you look at the literature around arsenic in skin. And it's a consequence of chronic exposure, but generally through absorption, through drinking contaminated water. So these are pictures. Basically, it starts with this hyperpigmentation. It looks like a raindrop pattern. And it might be white or black markings in sort of a mixed bag, but classically looks like raindrops on skin, these increased pigmentation, and then they become papules. They sort of become keratotic papules, so they sort of get thickened and they can coalesce and becoming larger papules, and eventually these become nodular. So from just a flat melanosis, papular nodular lesions over time, and they get from small little 1.2 centimeters to large, more than 5 millimeters, more than a centimeter in size. So from just initially a small diffuse thickening to large varicose papules and plugs. And again, the risk of cancer. So this is squamous carcinoma. And there's a squamous carcinoma that has evolved within background lesions of arsenicosis. So the risk of cancer is significantly increased if you have arsenicosis. Then there's this classic description of Mees lines, which are white bands across the nail bed, racemic contrast. So now the interesting thing is, do we see this in the occupational setting? Pinto McGill, no. And at the smelter to which I'm describing, also there seems to be not much of the seen. I'm not sure how hard it's been looked for in truth, because the medicals are done by OMPs, but they're trained, yeah, which means they will definitely find them if the lesions are there. But in support really of the point made by Pinto and McGill, and I think perhaps this might have a role to play. I had a good look at the literature on skins and exposure through groundwater and what have you. And lots of studies have shown that skin lesions, we're talking about groundwater, hey? Skin lesions start happening at exposures of less than 50 micrograms per ml. But in fact, the study done by Smith shed perhaps some light on it. Basically, what Smith and their group did is they looked a lot more carefully at the long-term exposures, and they stratified it more carefully than what looked like done in the previous studies. And this study was basically showed that you really do need a long period of exposure, sort of an average latency they found in their study of like 20 years, and of values in the drinking water greater than 100 to 200 micrograms per liter. So a long time long latency, lots of exposure to get this sort of stuff, as opposed to in the occupational setting, which there are people exposed obviously for 20 years, certainly even in our smelter that I'm talking about, but we're not talking about simply this level of exposure. So this is what we're talking about in terms of the public impacts, and this is where you'll see thousands and thousands of publications, and it's a quick run through this. Back in the 1920s in southwestern Taiwan was the classic first writings on public exposures, and this is where that black foot disease was described as a result of peripheral vascular injury, and you get ischemia in the peripheries as a result of exposure to chronic exposure to arsenic. Basically, they were digging these artesian wells as a water source, and what was happening is they were digging it down into groundwater sources, which was high in arsenic, and over a period of many years became chronic arsenic exposure became endemic. In 1957, river water was rediverted, and it went from essentially to bring water closer to the people in the small city, and that rediverting of water carrying natural arsenic in it resulted in the drinking water of over 250,000 people getting excessive exposure. And again, massive studies there were done showing high rates of cancer and mortality. Bangladesh and India are probably the largest groups of exposed people in the world. We're looking at 42 million people in Bengal and 100 million people in Bangladesh exposed to high levels of arsenic and doing the sort of stuff for which I speak. So you understand now what the World Health Organization is making a fuss about this. And apart from the skin, of course, lots of the organ systems, and this is just a quick stat to say all organ systems are affected by these chronic exposures. Right. So what did we do? We wanted to find out something about people and their behaviors. We wanted to measure the chemicals in the materials used, and then we also wanted to see something about the skin reactions. So through the questionnaires, we felt it was a retrospective case control study with controls matched. Essentially what we did was we said, you're a case, and what I didn't have written here is the cases where people had an incident of last 12 months, and then we matched that person in terms of drop time with a person who hadn't had a rash in the last year. So retrospective case controls matched, and they were sort of 1-to-1, one case, one control. We then looked at the actual what's in the dust, which is an exposure characterization study, literally looking at the chemicals in order to determine the exposure response analysis, or at least to help us understand it. And then objectives 4 and 5 were again a retrospective case control study looking at how people were exposed and how did they react to the skin reactions. Variables measured, so the potential determinants of skin reactions, what was in the dust, how did they react to it, and then histories of allergy, previous rash, how long they worked in age. Independent determinants of the skin reactions, weather, use of PPE, skin hygiene, and then potential confounders. We wanted to check what about other dermatoses. So we had Gail there, fortunately, to examine these people to have a look and see whether any other dermatoses that could potentially be confounding our inquiry. And also to be absolutely certain that Greg's getting it right in terms of what's allergic and what's not allergic. So the chemical lab assessments, we looked at the workplace constituents of what's in those dusts. And we then standardized that in order to use it for patch testing. I'll need to explain that briefly too. And then we did these clinical assessments through a questionnaire, Gail did an examination, and then the patch testing. And in those questionnaires, we looked basically at briefly at socio-demographic data, such as age, etc. Something about the history of allergies in particular is what we really wanted to know. It's a short questionnaire aimed particularly from a medical history point of view of their allergies. And then we asked them about how they look after their skin hygiene practices, the use of PPE. And then we had a small subset of questions for those who were just cases to find out if there was something about the features of their rash that would be informative. So it's a case group, total group of around 50 or so. 25 was the original planned case and control. Now, this is a small sample size for sure, And I remember Mohammed was expressing some concerns about that, but really the patch testing is such an onerous procedure. We just couldn't have access to more cases than that for the purpose of patch testing. You see that, in fact, these 50 cases were done over 2 sessions, and it's a week each time. It was a week at the plant to do the first 25, and then a year later to do the second 25. So that was a significant limiter. So those who were cases were those presented who had a rash in the last 12 to 24 months, and then purpose of selection of those who worked in the same job as a person who just had a case but had no rash. So they were identified in advance, and on the day of the testing, each one on our list was then sat down, invited to participate in the study, and those who agreed then signed a consent form. Those who declined, and there was one, there's always one, I guess, who said no, he didn't like the idea of having stuff stuck on him and decided to decline. And it was a control. But interestingly, there was such excitement in the plant that 2 people said, yeah, pick me. So we said, fine. So we ended up with 27 cases and 24 controls. So this is just a reminder of the consent, the questionnaire. The questions around allergies were developed with a lot of help from Gail in order to try and get some sense of the background, allergies playing a role or not playing a role. I think inevitably you will see towards the end is that the 25 questionnaires in a study of this nature is going to struggle to give you statistical strength in a questionnaire study. So that is the big limitation of what we achieve. Patch testing, has anyone done patch testing in the room? I've got to tell you, it was a wonderful experience for me. So you're all experts in patch testing. Oh my goodness, we hadn't in our day. And I was excited by this idea, but a little bit unnerved, I've got to tell you. Anyway, so I didn't explain to you, but basically, a quick reminder, you need these materials. Basically, these are collection materials into which you put in these dilution things. So you have to arrive in advance with all your kit, with these wells, strips with wells in, and all the paraphernalia that goes with that. You need to be able to mark where you put it. You need to be able to clean the area before with something just to get rid of some of the skin grease. So we needed some of that. So first you clean, then you put the sticker on, and then you leave it on. But of course, before, the big job is the preparation of the actual materials, which I'm going to talk to you about. So on each day, Monday and Tuesday, we prepared the materials for testing. So put the strips out, open them up, and put the solutions, the dilutions onto the strips, and then applied them. And then from Wednesday to Saturday, we then reviewed people come back and back. For the first 24 hours, we just said, come back and tell us how you're doing. And then at 48 hours, we removed the strips to see what was going on. Just a point about this 48, 72, 96. We're looking for the difference between contact allergic dermatitis and contact irritant. Allergic is delayed sensitivity, so therefore we'd expect the response to happen only from about 48, 72, even 96 hours after the event. So you can see 96 hours is a long sit. There we were till Saturday at the smelter. Everyone else had gone home, and Gail and I were suffering through these last 2 cases. So that's the sequence. We had these collection forms. This is one populated. This is the workplace allergen form supplied by the people who supplied us with the strips, with 49 of the allergens that Gail has developed over years and years and years that are useful for workplace allergen testing. And then I had to develop a handwritten one. This is Greg's handwriting, where I then populated the irritancy, yes or no, under Gail's advice, at 48 hours, 72 hours, 96 hours, with these dilutions. So this is the control water for the different smelter materials. So this is the arsenic plant, the smelter converter, and the ETP. Each of those obviously had to then be prepared in advance and compared with water. That's neat. I'll tell you about this in a moment. And these are dilutions. And then these were read at 48, 72, and 96 hours. So this preparation thing was a big deal in this. One of the big delays was getting the preparation right. So firstly, what's in the workplace test sample? these are the 4 sites from which the samples were collected: the arsenic plant, the baghouse, the converted baghouse, and the ETP. And this is the percentage arsenic in there. So it varies from 98%, pretty much pure arsenic in the arsenic plant, remember that's what they make, down to only 5% at the ETP. Now, how do you deal with that when you're going to compare apples with apples? So you standardize, which I'll explain to you in a moment. But basically, this was part of the delay is that the smelter QA lab was supposed to give me this analysis, and they did, but they didn't do a particularly good job of it. And it took us months and months to realize that it wasn't going to happen. So we ended up by getting Chemtech Lab to do this formal analysis for us. But that was a big delay in getting this result back. It's a point, therefore, to note that these were not the exact samples that were used for patch testing. The exact samples for patch testing we did by the QA lab on site, who said they could do it for us, but they ended up by messing it up. So we used similar samples from the same workplaces, and I'm comforted to say that these are bulk samples from a continuous process that really had very little change over time. So we felt comfortable that what we see on the screen is a reasonably representative example of what was happening throughout the year. So we analyzed these and came up with those results. The important thing is 2 things. One is the variation in arsenic concentration, which needed to be standardized. And then the recognition that in ETP, at least, there was a fair amount of lead and sulfur, which are potential irritants as well that we need to bear in mind. We had a look at the pH of these, and the pH of the arsenic plant is quite low. This was before standardization, okay, and this is after standardization. And I'll talk about standardization in a moment, but basically you have to dilute these substances so that they all have the same amount of arsenic. And so before and after, you've got differences in what's actually going on in the 4 samples. But the important determinants from an irritancy point of view is the pH. So we had a pH essentially of the test samples that were put on skin. And interestingly, the R-smelt and the converter had alkaline, quite strongly alkaline. These 2 here are formally measured in the lab. 8s and 9s, pretty much 9, 8.8 and 9 for these 2 baghouses. And then just before sticking the stuff onto people, Gail did a quick litmus test to be sure, which agreed quite comfortably, 8.5 versus 8.8, and 7.87, with what the lab found. And why I mention that is because for some reason we could not get a pH on the arsenic plant's materials. And one of the reasons is because the arsenic plant closed in 2017. So they had stopped collecting it and measuring the pH, and so we were reliant on the measurement we did on the day, which is 4.5. And therefore tells us that was quite acidic in nature, which is irritant in itself. So the need to standardize, and I'm sorry about this tedious long notes here, but basically we want to know about arsenic trioxide. So if the percentages in the different products have varied from 5 to 98, you've got to standardize that. So basically what you do is you then standardize by diluting them all down to a particular standard value. And we chose 2 grams per 100 ml as the target for our standard. And the reason for that is in fact the solubility in water, 2 grams per 100 ml. So we then did this calculation and said if 98%, 82, 20, and 5%, then 2 grams in 100, 2.5 grams in 100, 10 grams in 140 grams. We'll reduce this to the same amount of arsenic. So at least then we were comforted that in these bottles of neat, they all have the same amount of arsenic in. They have, of course, there is an implication on the non-arsenic components. So if you look at this little table here, if you look at the arsenic content of the arsenic plant and the various others at 5, 20, 80, and 98%, this is the multiplying effect of that dilution brings about to the non-arsenic stuff. So the arsenic is now the same for everyone, but on the ETP, it's now 18 times more impact on the non-arsenic components. So remember, that was where there was a bit of sulfur and lead in the ETP. So of course, that was a little red flag for us. We thought, what's it going to do? And we'll have a look at it in a moment. So it amplifies the relative contributions of the non-arsenic components. And just a quick reminder that the pH was also done on these after the pre and post standardizing. And interestingly, the pH didn't change much from pre and post. So that we found curious, but certainly we do know that the non-arsenic components will be affected. So finally, then you establish increasing dilution. So this is scale with the lots and lots of little green bottles, because you've got, of course, the different samples from the different sides. There's your neat in the blue, and then the dilutions from neat to 1 in 10, 1 in 100, 1 in 1,000, and then water. And that then gets prepared on a daily basis, ready to go into those strips. So there the strips are. There we are testing the litmus, putting it into these wells, and any breeze that happens to rush through, or someone walk past, and there goes, you know, the piece of absorbent material that is lying inside the well. So any of you, as I said, who've done this will know the pain and suffering. But there, this is what a back looks like when it's got all of these on. These double strips are the strips of the standard allergens that cause allergy, and these are the ones that we wanted to know, are they irritant or allergic. These are from the plant. These are just the ethics approvals from UCT and from the Department of Health in Namibia. So let's gallop through these results. My apologies.
If you have 10 minutes.
Yes,
Do you
exactly.
have any questions?
Pardon?
If you still want questions, you have.
Yeah, I'm going to gallop as fast as I can. So this is basically the results from the questionnaires, which I'm going to speak through quite quickly because the questionnaires ended up by playing a relatively small role in the study because there were just too few to be useful. But the gender distribution shows 90% of people are male, which is pretty much the workforce because it's a carcinogen and teratogen, crosses the placenta. And there's a little bit of survival effect, although there were only 5 years in service. So these are not people with long-term chronic exposure. So a little bit of survival effect. The controls 42 years of age, cases 35 years. And the medical history in terms of reporting allergies, basically no different between cases. So this is the people who are self-reporting pre-existing allergies to anything, where the case and control pretty much the same. And then these are the ones that are diagnosed by a doctor. Did a doctor say you got eczema? Did a doctor say you got this? And again, no statistical significance, although curiously, for some reason, there was more eczema in the case group, in the control group, and more urticaria in the history. So, but again, not significant statistically, and the small numbers. And then this is again self-reported again to allergies to metals. Do you have an allergy to zinc or nickel or what have you? And again, no statistically significant result. But in fact, the case group did show 3 times higher numbers of respondents. See there, 28% of cases saying yes, they responded. Yes, they thought they were allergic to some sort of metal, whereas only 8% in the controls. So small numbers, not significant, but certainly looks like something trying to tell us there. And then the workplace skin management and hygiene practices. So here we're looking at hand washing at work, average number of times you wash per day, the use of soap, washing before going to the loo. Because in other words, if you don't wash before going to the loo, you might introduce dermal contact with stuff on your hands, and then the use of cream. And they're basically on all of these results, cases and controls, pretty much the same. Peak was 1.7. So there was no difference between the two groups. And there may be biases here in terms of what people are saying about their hand washing. There may be bidirectional biases. In other words, they don't want to say to these researchers that they're not washing their hands both ways. So I suspect that was maybe playing a role. And I think if we were to do this again, we'd structure these questions a little differently. A, we'd have more of them, and B, we'd maybe structure in a way that we really do need to reassure. I suspect the people doing the inquiry were not providing enough reassurance that the results were confidential and the results were not going to put anybody at risk. So no difference. And the PPE used pretty much the same. Do you use this PPE? And these were the list of PPE used, and how often do you use it and how many hours a day? And again, no differences between cases and controls in terms of the use of these. So the cases did not spend more hours a day in a particular given piece of PPE. Pretty much the same. And so there were some poor responses to the mutton cloth mask. You see over here, only 8, only 4, and I think those are because those were just badly asked questions, as badly structured questions. They were difficult really for the person to understand. So the factors relating to the occurrence of rashes in the cases only, we will want to know about weather. And there's basically none of these was statistically significant, but there was a hint that hot weather, dry weather, 21-to-1 responses, 12-to-1 responses, showed that basically dry and hot looked like they were sort of background reasons for a high risk of the likelihood of a rash. But there was, if you look here again, the respondents were relatively impaired, 14 out of 27 responses, 13 out of 27. I think there was a memory bias playing. And then what about use of PPE and the contributory role? Pretty much all along here, helmet, overalls, goggles, gloves, boots, respirator. But the respirator did seem to stand out as a driver for the most frequent cause of problems. And the distribution, again, head and neck, the face and respirator area in the neck are the most areas up here was the most likely cause of the rash. And let's go quickly onto the rashes themselves, because this is really where some of the sexy stuff is. So just a point then, the clinical nature of the skin reactions. I've talked about irritancy already, but basically these are what irritancies look like. You're going to have a reaction quite soon, and you were looking for a dose-dependent reaction. So this is neat, this is very dilute, and you can see how you get more reactions under neat and fewer reactions as you go down with more and more dilution. And you get basically these inflammatory reactions, the pinkish color change, pus-containing vesicles, a little bit of these brown spots here are damage and necrosis to the tips of the these papillary reactions. So these are classic, what look like skin burns, essentially, which is an irritant reaction, which is dose dependent. And here's where the first important finding. So let's just show you what this is saying. What we're analyzing is the arsenic plant, the arsenic, the converter, and the ETP, and the proportional reactors. So how many of them reacted positively and negatively. So this is number of positives, this is number of negatives at that dilution, and so from neat to very dilute, neat to very dilute, and so on of reactions. So basically the irritancy, we use the prevalence of reaction as a marker of irritancy. And you can see the arsenic dust and converter dust is much more irritant. These two generally at neat down to very dilute, neat to dilute, the arsenic and the converter more so than the ETP and the arsenic trioxide. So generally there was a difference there. But these could all be because of pH. If you remember, the pH is very high here in arsenic and converter, and the pH is very low here. Interestingly, though, yes, that's the important first thing, is the ETP was pH neutral, and yet it had a very similar reaction to arsenic trioxide. So even though it's pH neutral, the other observation is that arsenic as an independent chemical compound is irritant. There's a proportion of irritancy similar to the ETP, so it's independently irritant. But this could be either arsenic as a toxic substance, or it could be just the low pH. Remember, pH of 4.5. Then, if you compare the arsenic plant and the arsenic, here, okay, remember the standardizations are quite similar. This one here says 98% arsenic, 82% arsenic, so very similar, really. And yet, there's a bigger reactivity to arsenic than arsenic alone. So clearly, this pH of 8.8 is playing a big role in addition to the arsenic. So there's similar arsenic in both, but the pH is more over here, and therefore this reacts more. If you compare the arsenic to the converter, these two, all right, the dilution here is much higher. Yeah, this is a 28% arsenic, 82% arsenic, so therefore this must have been much more diluted, yet very similar reactions between the two. Same arsenic content, similar reaction, but different dilution. So the non-arsenic components were different. But there's similar pH. So the similarity in pH here between these two are probably the key drivers in those different reactions rather than something else. And remember, the arsenic had that level of reactivity on its own. And if you compare it to the ETP, very similar reactivity. This is neutral for the same quantity of arsenic, pH neutral, pH low, but the same arsenic. So if you compare this the arsenic plant and the ETP, similarly irritant, but this is pH neutral, the same arsenic in it as that side there. So it suggests, therefore, that whatever arsenic is coming in here is in itself inherently irritant, regardless of its pH. So whatever the pH role was happening here, that's neutralized here because the pH is neutral. So that told us that it suggests that arsenic on its own is probably irritant on its own. However, of course, we do recognize that there are non-arsenic components in here that were amplified by the dilution and the standardization. Here in the ETP, remember this was very, very least diluted because arsenic is only 5%. Here it would have been much less diluted, so the non-arsenic components would have been relatively amplified. So clearly they're playing a role. But if you look at the difference between this and this, the non-arsenic components, even though they were amplified by 17 times, seem to be playing a relatively small role in the difference between these two. So we felt that this combination of findings gave us sufficient reason to believe that arsenic is independently irritant. It's irritant probably because of its inherent irritancy plus the pH. And that for these two here, it was basically arsenic plus pH that was causing irritancy. With no evidence here of allergy. These are classic dose-dependent shifts. It's a graduated response, classic dose-dependent, which is what you find in irritancy. This was cases only. This is cases and controls. No real difference here. I'm going to skip on because we're down to the last few minutes, but nothing really yet to write home about. And this is controls. People who've never had a rash. So I just want to make the point, look at these. This basically looks pretty much the same as cases and controls, identical. And we actually formally tested that statistically and showed that cases and controls for all the variations in dilution were statistically the same. All of these are pH values, P values of 0.5. So basically no differences in the reaction rates. So in the last couple of slides, and just to quickly talk about the skin reactions.
Wrap up.
All right. We're done with the 5 minutes, eh?
Otherwise we won't have time
for questions. So I'm going to just wrap up then. These just to show that this is what classic dermatitis looks like. That's contact dermatitis. There were people who reacted to the contact allergens. There were relatively few, and most it was wood tar, nickel, and fragrances. And there was no difference between cases and controls, although it looked like the cases were slightly more. The people who were cases maybe more reactive, but not statistically. So these are the limitations, basically the sample size. The response to the questionnaire wasn't really happy with. There's all the issue about the testing of the bulk samples to make sure that what's in it, what are we putting on these skins. That was a challenge to get right. Because it wasn't exact samples that were patch tested, but the samples that we did the analysis on. The potential for misclassification was quite low. We pretty much knew irritant versus allergic. We had Gale there, but four of the participants got their stuff wet, and that all was flapping in the breeze when they walked in. But fortunately, only 4. And that's the concluding comments, is that it's an irritant, not an allergen. And all people are equally affected. So there's no subset of vulnerable people. Therefore, medical surveillance doesn't have to target special people. So no differences between case and controls for skin hygiene practices, but that doesn't mean you don't have to have good hygiene practices. There's still a mainstay. You must abandon the protective hand cream because it played no role. I mean, it's the hands of only 6% of skin reactions anyway. And that's it. Just one last thing about the RPE, restricting the sprite protective equipment. There's this clean shaving policy, which has been amended to not being quite so clean shaven because it created more trouble when it was worked. Questions?
Thank you. So you can see who is online.
Yes.
Thank you, Greg. That was really, as we all can appreciate, lots of information and a wonderful experience with interesting results. So questions from, we'll take, before we go to questions, I know Johnny is still online. Johnny, would you like to comment before we have any questions? as the
No,
supervisor?
no, I think let's get questions because I don't have much to add.
Okay. Thank you, Johnny. And I don't see Gail. Oh, Gail's here as well.
Yeah.
Gail, hi. Would you like to comment? You can unmute. Seeing any movement there. Okay. Questions from the room here. Would anyone like to ask any questions? Shamira?
What are some of the prevention things that one could consider even in findings? Because there seem to be the total difference in terms of the risk of all places.
Yes, so look, I mean, the analysis in terms of the risk that was given to us through the questionnaires were, I think, quite limited in value in the end. So, but what we could draw from the inference we could draw is that the preoccupation with the hand creams and those sorts of things was misguided. We could see that the PPE is in fact playing a role, even though it wasn't statistically significant. If I were to share some of the images with you of what it does, you know, that those respirators creates a lot of irritancy around the contact points. So the change would be valuable if they'd stop wearing them. In other words, reduce the exposure to the point where we're RP. And it's a drive. I think the smelter have set essentially a target of being respirator free, which would be a very useful step. The exposures in the last few years that I've been there are enormously reduced. So they are along the way. They've upgraded the smelter. It's a national modern place. So the prevention would be exposure and then the use of the PPE. I think that would probably be the main thing. And then even while they're using the PPE, this preoccupation with clean shaven policies really sort of magnifies or amplifies the impact of that skin contact. So a little bit of shaven hair is actually okay.
So I had one question. Did the company do biological monitoring? And if so, what were the results?
Yes, of course, I've got 18,000 biological monitoring results, which are absolutely, for any person who likes statistics as I do, tremendously useful. So we've done extensive monitoring over the years, and they show the levels were really high when we started 10 years ago. The levels are now sitting at about, they use the TLV as their target. So the averages are sitting at about TLV, but that's the average. The 95th percentile is still sitting above TLV on average, and there are pockets. So particularly the people, what we found is the artisanal people who are involved in breakdowns and repairs, they're still sitting with higher levels of arsenic. And they have a rotation policy for them. So if they pick up a high level of arsenic, they get moved out and rotated. But the plant has gone from an average level that was probably 3 or 4 times TLV down to sitting at about TLV on average.
So were you able to look at any association between the arsenic levels and the presence of the rash?
We didn't do that, Mohammed. It was one of the other things. And one of the reasons why is that we weren't looking for arsenicosis. We weren't really looking for absorbed systemic effects. We were looking for contact allergy and irritants. And so we felt that to combine, we could have, of course, I can look up those people at any time and see in my database what the exposures were, but it wasn't really part of the inquiry. It was not systemic absorption and therefore arsenicosis. We were looking at contact.
Good. Are there any questions from the online audience? I don't see any hands. Anyone wants to make any comments? Questions? No.
Sorry, just
Yes,
just
please
realized,
go ahead.
it's a good point. I just realized I used the wrong term. I should have used BEI, not TLV.
Right.
We've been monitoring the BEI. The
BEI.
TLV, the total exposure, the exposure to air were obviously way above TLV.
Okay.
And they were very reliant on their PPE to bring down to the BEI, the biologic exposure, which is what I've just referred to, Mark.
Because if you had high levels, ambient levels, it is probable that a lot was also settling on the skin, and that's probably why your cases and controls had also the rashes, because they were also exposed just by general airborne contamination.
Yeah, all over. In fact, there's arsenic generally settled on roads and pathways and around the plant.
I don't see anyone. I just also had an experience many years ago. I was called to a gold mine in Mpumalanga, and workers were complaining of a rash. And so we went out there and we found that workers had the classic manifestations of the skin rash, and they also had lots of ulcers and nasal perforations. And the workers thought that it was because of the water they were drinking. And after doing and the company said that it's unlikely to be due to the exposure. And we then did a walkthrough and we found that arsenic is a byproduct of gold, of this gold process. And they were storing the arsenic in big bags in a shed. And when it rained, the bags all got wet, and the water with the arsenic was contaminating the drinking water.
Wow, okay.
And so infants died because of arsenic poisoning.
Yeah.
But also the workers were exposed by virtue of the process in that gold plant.
Yeah.
And their levels were also very high in terms of exposure. Shahida?
This one, so they showed some studies which shows an increase of cancers linked to ingestion. I'm wondering whether this type of category is at risk of cancers long term,
Really?
and whether there is
Yes.
a rational or case can be made, especially post approval surveillance. Is the problem going to develop much later if they are going to develop?
Yes, indeed. So, in fact, that question was asked, partly driven through us in sort of my consultative role. And so what we did about 7 or 8 years ago, in fact, done by Dave Rees from NIO, we got them to come in and do some medicals, quite a comprehensive set of medical surveillance, including radiographs and bloods and what have you, on all takers. They basically put out bulletins on the radio. They told everyone from the deep swamps of the Okavango, or wherever you are, come in and have a medical, and found no, in fact, increased cancer rates, interesting, fortunately. But it remains on the radar totally all the time. So part of the medical surveillance strategy is a lot like asbestos. So they get a regular radiographs and the like, and skin examinations, bloods and what have you. And obviously any passive surveillance that we found one case that I know of a nasal ulceration. Again, that was found through passive surveillance, not through the monthly thing. But you're absolutely, carcinogenesis is the top worry all the time, as part of the surveillance strategy.
So is it related to the valency of the arsenic, whether it's in the trivalent or the pentavalent form?
There is
the arsenic, the carcinogenic potential.
All I can say is that I think V3 is less. The pentavalent is more toxic than the trivalent. And they use the word toxic. I'm not sure if that necessarily means carcinogenesis. But in fact, anyway, when you absorb it, the body immediately converts V5 pentavalent to trivalent straight away. It's an immediate, and then gets methylated. So I don't think it really matters what you're exposed to, because your body methylates and reduces lots of acid very quickly.
And do you know whether people eat a lot of fish in that part?
They do, yes. So biological monitoring course had to be modest, changed accordingly. So the original strategy was just total arsenic. And it's now, of course, what we call amalgamated. We have to create a new name for it. So total arsenic minus arsenobeta and arsenocholine to give you the residual, which is what we call amalgamated arsenic. But that's expensive. In fact, we did quite a lot of speciation a couple of years ago, formal speciation between pentavalent, trivalent, and the monomethyl, dimethyl, and the proportions. Because one of the concerns was, is methylation, genetic methylation, a risk factor for that particular population? And we did probably several hundred of those, and showed that, in fact, even those that were very high exposed and those that are relatively low exposed, the proportions of MMA, DMA, trivalent, pentavalent were all retained comfortably. Because what would happen is if you get your system of methylation flooded, you'll then start finding your proportion of trivalent and pentavalent higher in the urine and your methylated relatively lower. The study showed that if those proportions stay correctly, what they should be, which is about 80-20. So, yeah, a lot of interest went into the biomonitoring. And
Can I just make one point about the cancer?
Please go ahead, Johnny.
You know, the problem, it's like South Africa. There's no cancer registry. So it's very difficult to monitor any excess cancer occurrence. So that's just one thing to bear in mind. And that's like a worry in the background.
Thank you for that. Are there any other questions? No, I'm not seeing anything online. Thank you again. Thank you, colleagues, for attending, and thank you, Greg, for that very interesting and thought-provoking presentation. And all of us here can appreciate all the challenges that goes with research, but I'm sure at the end of the day, it has been a rewarding and thought-provoking and journey for you, and I wish you all the best with publishing.
Thank you. Well, just a thanks again, please, to my long-suffering supervisors, to Johnny and Gail, particularly both of you. Gail and Johnny have been up to this plant to go and have a look, and certainly Gail's patience with Greg, the dermatology student. So thank you again, both publicly, for your tremendous support in getting this done.
Great. Thanks, everyone. All the best. Bye, everyone.